welcome to Model-Based Inquiry. In this video, we'll explore how to use our MBI Unit Development Template, a tool designed to help educators design rigorous, phenomenon-driven science units grounded in modeling and inquiry. It can be used to design units at any grade level from elementary through high school. We'll walk through each of the 5 stages of an MBI unit using a real example, a middle school physical science unit titled From Baking Cookies in Cars to Urban Heat Islands, the Physics and Inequities of a Warming World. The template is structured around 5 stages: planning for engagement with important science ideas, eliciting ideas about the phenomenon, negotiating ideas and evidence through tasks, building consensus, and establishing credibility. Each stage includes guiding prompts to help you design instruction that centers student sense-making, scientific modeling, and constructing explanations of real-world phenomena. You will notice blue links embedded throughout the template. These lead you back to the website for more information about the section, as well as to examples from elementary, middle, and high school units. On these pages, the green question marks lead to our support pages for the topic you're working on. Stage 1. Planning for engagement with important science ideas. The first stage of MBI focuses on doing the intellectually rigorous work of unpacking standards, developing an anchoring phenomenon and driving question, and identifying the important science ideas students will need to build a scientific explanation of the phenomenon. We also plan with the end in mind by constructing a draft model and target explanation to serve as learning targets throughout the unit. Our example unit builds from NGSS middle school physical science standards, such as MSPS 3 and MSPS 4, and incorporates data-driven tasks to highlight how heat is transferred via radiation, conduction, and convection, and how urban design and historical injustices shape who bears the brunt of urban heat. For the phenomenon, students explore why cookies can bake inside a parked car on a hot summer day in Phoenix, and investigate why extreme heat is experienced unequally across different neighborhoods. The anchoring phenomenon integrates key concepts in thermal energy and radiative transfer with social studies of heat inequity in urban environments. The target written explanation and example final model help clarify the goals of our instruction. While students will construct their own models and explanations, creating them ourselves helps us better understand the underlying science ideas and the instructional targets. Stage 2. Eliciting ideas about the phenomenon. This is the first stage enacted with students. It begins by introducing the anchoring phenomenon and driving questions, and inviting students to share their initial ideas and lived experiences. In this unit, students begin by watching videos of people baking cookies in a car. Then, they discuss their own experiences with heat, especially in their neighborhoods, and consider what might cause certain areas to be hotter than others. In groups, students generate and share initial hypotheses like, it has something to do with the windows trapping heat, or some places have more trees than others. They also construct initial group models using arrows, labels, and magnified views to show what they think is happening to heat and air inside the car and in the environment around it. Importantly, the groups share these models with the whole class to make sure everyone's ideas are resources for everyone else. Stage 3. Negotiating ideas and evidence through tasks. This is the heart of the unit, where students investigate questions, test their models, and gather evidence through purposeful tasks. Each task is aligned with a core science idea and coordinated using a summary table. In the example units, students conduct an infrared thermal mapping investigation around their school, heat soda cans using solar radiation to study conduction, observe convection in water and air using colored liquids, use simulations to understand how car windows trap infrared radiation, and investigate how race, income, and urban infrastructure influence who is most affected by extreme heat. Midway through, students revise their models and hypotheses based on what they've learned so far. After each task, the class fills out the summary table to come to consensus on what they learned and how it helps them explain the phenomenon. Even though we construct the summary table together as a class, we first create a draft version in the template to help us think through possible responses ahead of time to make the facilitation of the discussion easier. Stage 4. Building consensus. In Stage 4, the class works together to finalize models and synthesize ideas. Students compare their revised group models and work to construct a shared class explanation. In the example unit, This includes finalizing group models and facilitating a consensus-building discussion before building a gotta-have checklist, an agreed-upon list of scientific ideas and supporting evidence essential for explaining the phenomenon. This stage reinforces the idea that science is a collaborative, iterative process grounded in evidence. Stage 5. Establishing credibility. In the final stage, students craft individual evidence-based explanations of the phenomenon. These are peer-reviewed, revised, and submitted as a summative assessment. In the example unit, students draw on the checklist and summary table to explain both why cookies bake in cars and why urban heat is experienced differently across communities. They support their claims using science ideas and evidence from the tasks. In the template, we create a draft final evidence-based explanation at a level we would expect from our students at the end of the unit. The evidence-based explanation builds on the target explanation from earlier in the template by including specific evidence students will gain from the tasks. Finally, we facilitate a peer review session where students provide feedback to their peers based on specific criteria. Students use the feedback to finalize their explanation to turn in and be evaluated. We have developed a rubric for the students' explanations for your use. To get started, click on the link below the video to make your own copy of the template in Google Docs. Use the prompts as you go and feel free to adapt the structure to fit your classroom context. You can also download the template as a Word doc or PDF. And be sure to check out the completed version of the Baking Cookies unit on our website. This template is just one piece of what model-based inquiry has to offer. If you're ready to design equitable, practice-rich science instruction, we hope this helps get you started. Explore our site for more resources, sample units, and instructional tools. And if you create your own unit using the template, we'd love to hear from you.